Hi, and welcome to Earth Science Online. Today we're going to be talking about minerals. So let's go ahead and get started. Let's start with the definition of minerals. So what are minerals? Minerals are naturally occurring inorganic solids with specific chemical composition and a definite crystalline structure. So let's break that down. So what does that definition mean exactly? So naturally occurring and inorganic. So naturally occurring means that it occurs in nature. So it's just going to occur naturally, like salt, for example. Salt is a great example of a mineral. Salt is in the ocean. Salt is inorganic because it does not come from living things. It is just there in the ocean. Sugar would not be an example of a mineral because sugar is actually not inorganic. A lot of people think of salt and sugar as being kind of the same composition, but they're not. Sugar is actually formed by plants during photosynthesis, and so therefore it would not be classified as a mineral. Okay, so specific compositions. So it has to be a solid with specific composition, so not a liquid, not a gas. It has to have a definite shape and a definite volume. And each mineral has its own chemical composition that's unique to that mineral. It usually consists of one or more elements. There are a few minerals that only consist of one element. Copper would be a good example. But most minerals are going to be compounds of various elements. 2, 3 elements, sometimes more than that. Definite crystalline structure. So a crystal is a solid in which atoms are arranged in repeating patterns. So the atoms in minerals come together to form molecules, and those molecules are formed in patterns of, usually they're like triangular or maybe tetrahedral, and they come together to form these regular repeated geometric patterns. And so that is how we get the crystal structure. So to show you what I mean, let's zoom out here. And we'll talk about crystal systems. So when we talk about crystal structure, we're talking about crystal systems. So these systems are the systems that are generally accepted to be the crystal structures of most minerals. So you see here we have cubic, which is kind of a square, tetragonal, which is a little bit more rectangular, hexagonal, you see the 6 sides there, orthorhombic, monoclinic, so you see it's going to have kind of a leaning square structure. And then triclinic, it's going to have a leaning structure that you see here. The molecular structure on the inside is more triangular. You see that the 3 atoms there, but they come together to make this 4-sided structure that leans. Okay, so it's a little bit more rectangular than the monoclinic. Okay, so these are the generally accepted crystal systems, but they're not always readily apparent, so why not? So crystals that form in open spaces, such as this watermelon tourmaline here, they have readily apparent crystal systems. So if you look at this watermelon tourmaline, it was formed in an open space, and you see here we have all these nice, can't get my pen to come up. Drawing tool. We always have all these nice hexagonal shapes that are repeated over and over again. You can see that from the base all the way to the top. But here is another watermelon tourmaline, and it was formed in a restricted space. So that's going to be maybe in a cave, or maybe in a shell, or you know, inside of, maybe partially inside of a rock. But it's restricted. So that means that it's not this wide open space where it can just grow and form in this nice structure. So it's going to be, the growth is going to be a little bit stunted. So most minerals form in restricted spaces, and the crystal structures are not readily apparent. So from studying our open structure crystals, we know that watermelon tourmaline typically grows in a hexagonal structure. So we would know that this is hexagonal. It's just not readily apparent. We'd have to really study it and look at it closely in order to see it. So what else about minerals? So we know about the systems. Let's talk about composition. Oops, and I see that I have marks here on my screen. So composition, I told you we were going to come back to this. So mineral composition. So most minerals are made up of compounds. So that's going to be 2 or more elements in the periodic table. There are a few that are only made of 1. So examples are copper, silver, and sulfur. Those are single elements. But most are compounds, and I give you an example. It's quartz. So quartz is in this nice triclinic structure. You can see that it looks like the structure that we saw. This would have been grown in open space. Typically, they grow together. There's usually 2 or 3, sometimes 4. And quartz is going to grow in this triclinic structure because it has atoms that are covalently bonded in a tetrahedral molecular structure. So you see here, if we look at, this is the tetrahedral structure that the molecule is going to make. And we have these 2 atoms of oxygen and our atom of silicon dioxide. So here we have our 2 oxygen atoms up here, here, and here. And then we have silicon dioxide coming together. Oh, sorry, that didn't make it very good. It didn't do very well. Let me try again. The silicon dioxide, so we have our S and our 2 O's here. And we see our straight lines are going to form covalent bonds. So all of those come together and they make this tetrahedron. And then those molecules are going to come together to make this triclinic structure. So that's how the composition and structure work together with minerals. Okay. So now there is a range of composition with some minerals. So what I mean by range of composition is that the chemical composition can vary, but only within a specific range. So for example, olivine or peridot, as we know it as August birthstone, it has a chemical formula of magnesium or iron 2 and sulfur dioxide 4. So individual atoms in olivine may vary. Some forms may contain more iron than others. So you may have more of these iron and sulfur dioxide combinations than you do magnesium and sulfur dioxide combinations. But overall, the ratio of the total amount of iron and magnesium to the amount of silicon atoms in the olivine is always the same. So even if you have a little bit more of iron or a little bit more of magnesium, both of these together are going to be the same number as the silicon atoms. So that's silicon dioxide up here, that's going to be the same. So you're always going to have that ratio number. So even though there is a range of composition, it's considered well-defined because it has to be the same number of silicon as the silicon atoms. So iron and magnesium always have to be the same as the silicon. Okay, so let's talk about formation. Okay. So first, let's talk about mineral groups. So the most common minerals are referred to as rock-forming minerals because they make up most of the rocks found in Earth's crust. The vast majority of these are made up of 8 common elements. So you see oxygen, almost 50% of minerals have oxygen. Silicon is your second most common element, followed by aluminum, then iron, calcium, sodium, potassium, magnesium, and other, which are going to be just various different trace elements. So mineral groups. So here are your main mineral groups that you see. Silicates make up 96% of the minerals in Earth's crust. So an example of that would be feldspar. Another example would be quartz. Silicates are going to have silicon and oxygen. composing them. Carbonates are minerals composed of one or more metallic elements with CO3. So that's a primary mineral found in limestone and marble, calcite, dolomite, a lot of different examples there. And then finally, oxides. So those are going to be compounds of oxygen and a metal. So oxygen, aluminum, oxygen, silver. Here's some examples: iron oxides and magnetite. And magnetite is aptly named because, as you can see here in this picture, you can see that these paper clips are actually sticking to the magnetite. It has magnetic properties. So that's really all you need to know about mineral groups, is that you have those three that are the most common, but you have other minerals as well, but your three main most are going to be those. So how do minerals form? So one way that they form is through magma. All right, so from the cooling of magma, which is a molded material found beneath Earth's surface, we've talked about this, it's found in the mantle, that when it cools, it can form minerals. So density differences force the magma upward toward the cooler layers of Earth's interior. So you're going to have the more dense materials are going to be rising up, and the less dense materials are going to stay down. And the type and amount of elements that are present, as well as the rate of cooling, are going to determine which minerals form. So, oops, sorry. So, large crystals are going to form slowly. Why? Because cooling magma has more time for those elements to arrange themselves into large crystals. So those repeating patterns, they can repeat over and over again and make those larger crystals because they have time to do that. If you have quickly cooling magma, however, small crystals are going to form because once they come into contact with air or water, that's going to cool them off pretty fast, and so the elements don't have time to arrange into large crystals, so you're going to get your smaller crystals from your more quickly cooling magma. So when you see a large, if you see a crystal that you know is formed by magma, you can know if it was slow or fast based on the size. Another way is solutions. Minerals can be formed by solutions. So mineral forms in what's called supersaturated solutions. And I know that we talked about this a little bit when we talked about atmosphere. A given volume of water can only dissolve so much solid before it becomes saturated. So minerals precipitate and form solids out of the solution. So they come together, and because they can't dissolve in that water anymore, because it's come to that maximum amount, these minerals are going to come together and they're just going to come out of the solution as solids. Another way that they can form is when water evaporates. So that's going to give you less water as well. And what's going to happen is the water is going to evaporate, leaving behind these elements that can arrange themselves into crystals because now they are supersaturated. So you either have, to begin with, you either have too many minerals, too many atoms in the water, and that is going to make it supersaturated. And so your minerals are going to form solids because there's just no more water for them to mix with. Or you're going to have the water evaporate from a solution, a mixture that's a solution of water and minerals that's equal. But once that water evaporates, you no longer have an equal mineral to solute solution. Instead, what's going to happen is those elements that are left behind are going to arrange themselves into crystals. All right, so identification. So, of course, the most noticeable characteristic is going to be color. but it is the least reliable due to the presence of trace elements within the compounds of the mineral, giving it its color. So an example is quartz. We have lots of different colors of quartz. You can have rose quartz, you can have smoky quartz, you can have all different colors. So that's not always going to be the best identifier, because you can have minerals that have lots of different colors because of trace elements that are present. Luster. Luster is the way that a mineral reflects light from its surface. So some are going to be shinier than others. Texture. That's going to be how the mineral feels to the touch. So it can be kind of soapy feeling, ragged, glassy. Streak. Streak is very reliable. The color of a mineral when broken up and powdered. It can be tested by rubbing the mineral across an unglazed porcelain plate called a streak plate. So this is an example. This is a streak plate. So you have two different minerals here. We have cinnabar and we have pyrite, fool's gold. So you see that pyrite, the color is gold. You see that here. You see that it's gold in color. But you see that the streak is actually kind of going to be a dark grayish black. So that's how we know that it's not gold, even though it may have the same color as gold. It's not going to be pure gold because it doesn't have the correct streak. Cinnabar, we see here, it's kind of a browny blackish color, but then the streak actually is a cinnamon color. So that's an example of how streak plates work. Now, hardness is another way that we can identify a mineral. It's the measure of how easily the mineral itself can be scratched. So the Mohs hardness scale is named for this German geologist. His name is Friedrich Mohs. And it's a scale in which an unknown mineral's hardness can be compared to the known hardnesses of 10 minerals. So these 10 minerals, with the exception of diamond, were selected because they are easily recognized and found in nature. So diamonds are not easily found in nature, but they were selected because we do know diamonds and because nothing is actually harder than a diamond. In fact, when we cut diamonds have to be cut with other diamonds because there isn't anything harder than a diamond. So you see here, if you look at the hardness scale, you see number 1, talc is going to be your softest. Then we have 2 is gypsum, and calcite, fluorite, apatite, feldspar, quartz, topaz, corundum, and diamond. So those are going to be what we compare our minerals to in terms of hardness. Most of the time they're going to fall in between, but it does give us a good general idea of kind of where it falls and what minerals it might be made up of. So it's a good starting point. So cleavage and fracture is another way that we can identify minerals. Minerals break along planes where atomic bonding is weak. So a mineral that splits relatively easily or evenly along one or more flat planes is said to have cleavage. Now, minerals that break with a rough or jagged edge are said to have fracture. So you can actually break a mineral and it can help you identify it. All right, finally, let's go to uses. What are they used for? So ore. A mineral is an ore if it contains a useful substance and can be mined for a profit. So for example, when you talk about iron ore, iron is a mineral and it can be mined for a profit and it's useful. So that's why we call it an ore. Ores are located deep in the Earth's crust. They're removed by underground mining. Ores near the Earth's surface are removed from large open pit mines. So if the cost of removing the waste material becomes higher than the value of the ore itself, the mineral will no longer be considered an ore. So it has to be profitable. So the two elements have to be there. It has to be profitable and it has to be useful. Another use for minerals that we all know pretty well are gems. They're prized for their beauty and their rarity. So not all minerals can be gems because not all minerals are rare. But like diamonds, emeralds, rubies, sapphires, they're going to be more rare, so they're considered gems. So now I want us to go to your critical thinking question. So if you look at the back of your packet, your critical thinking question is there. So let's take a look at this. So you have 3 questions. So first, explain why color is not a good test for distinguishing between pyrite and gold. What test is most reliable for identifying these 2 minerals? So if you go back through this presentation in your notes, you should be able to see what test is the most reliable for identifying the 2 minerals. Compare and contrast cleavage and fracture. Give an example of a mineral with cleavage and a mineral with fracture. And then finally, what is the hardness of a mineral if it scratches a penny but will not scratch glass? So you'll want to go back and look at your Mohs hardness scale there in your notes and also in this presentation, and determine what range it would fall into. Okay, so I will go over this with you in our next lesson, which is rocks. And then we will explore some more critical thinking questions about rocks. So thank you for joining me today, and see you again soon.